Right, good morning everyone. I know it's quite early, but let's go through a bit of a technical talk. Or that would be if I didn't pull a fast one on the organizers and decided to talk about another topic that may be interested all of us at some point, and that is how to occupy our days when we're working from home. I mean, the first thing is have a good Steam library, and let's hope we don't have any interruption. Actually, that might just be an interruption. That's the art director just pinging me. He has a great idea and he wants to have a call now. And yeah, let's keep on calm. Let's not panic. Because actually, that talk, I have some slides ready, and this is a survival guide to getting any effect in your game, so that next time your art director comes around with a great idea, you actually know what to do. All right. So I'm Thomas. I'm a graphics engineer, previously worked at Huawei, on Ubisoft, where I work on several console AAA titles. And yeah, you might have seen me last year talking about human rendering, or the techniques we used, or we might be using in the future. So go and check that talk out on the IGDC YouTube channel. And I'm currently at IEC Collective, where I make shiny pixels with other senior engineers, where we do consultancy for everyone. So if you have any open problems, open challenges in your game, just come and see me at the end. All right, so without further ado, what's that talk not about? It's definitely not a definitive guide to fluid dynamics. There's just so much to cover here that we're just going to skim the surface. It's not a definitive tutorial to Unreal Engine 5 rendering. We might be able to spend more than a day on this, but the organizers might tackle me to the ground if I keep on more than 45 minutes on that topic. So really, what that talk is about. So last year, lots of you approached me at the end saying how, we want to get started, but what's the resources? How do we even get started in rendering? How do we get started with our own effect? And to be honest, that's a problem I also struggle with. When I go to conference, when I watch talk online, I get super excited, burst of creativity, inspiration. I want to get started, and that's where I stand. Hello world, I don't know what to do, and I'm a bit panicked. Well, that talk is all about this. It's a guide to getting you on track with your next rendering effect, and give you tips and tricks on general engineering practices and how to overcome that fear. And because that is a very dry talk, if I just talk about this, we're also going to talk about fluid dynamics, compute shaders, Unreal Engine 5 rendering, and more importantly, shiny pixels. All right, so now let's jump right into the code. Well, that is actually what we would do if we want to fail. That could be what our art director had in mind, like fancy pixels. So when you shoot on the surface, there's that very nice fluid simulation effect. But before we actually start implementing that, we need to think about all the requirements, all the things that we need in order to do this. And that is an input system, right? We need to react to physics input and Unreal, but it's also about other systems interacting with it. Think about API. Maybe you want to clear the surface, maybe you want to refresh it, save it. All of these things, think about what other system will use in order to discuss with yours. But also think about configuration, right? Like your system is nothing, is your level designer, art people, or technical artists cannot configure it and use it properly. So they never want to play with just random files you drop here and there. So think about good editor integration that you can put together to simplify the job. But also think about visual requirements. It's not about creating like some kind of kitchen sink of a solution that does everything. 3D in that case makes no sense. You could spend days implementing a nice volumetric voxelized structure, but for that, no point. Go straight to the point. And finally, think about your technical constraints. Number of effects you have simultaneously on screen, or number of you need to keep warm. Simulate even though the player is not looking directly at them. And all of that ties into your budget that you're available. How many milliseconds you can use in your frame for your effect, because you need still to interact with other effects, except if you are actually doing an app that is just doing this on your phone. And a rule of thumb, and like small rule, very big sum, I like to keep in mind when thinking about budget is think about 1/3 of your frame for your shadow, 1/3 of your frame for rendering your color, your forward, your main image, and then another third of your frame that you can dedicate to post effects. Obviously, big sum right there. Next, that is something that many juniors don't do, and I'm really sad about this, but don't worry because a lot of actually very senior people don't do. It's collecting references, right? We do, as graphics engineer, a very artistic job where, you know, it's, if you go to your artist team and you say, hey, like, are you modeling a rock? They probably can give you a folder full of rocks, just images of rock around very different corners, just to know what to do. And as engineers, that's something that we often skip. So collect references, still images, images moving, but maybe also something that's not quite the topic, but tangential. You know, how does that color mix together? How does it flow when it's interrupted? Try to gather as much as possible. And you can use tools like PureRef, for example, but also ask your artists what they're using, because it's obviously better to integrate with their workflows and just come up with your own. Then I like to establish a little definition. That helps me understand what the problem is and better scope my problem. So in that case, I have this one. The key to fluid simulation is to take steps in time, and at each time step, determine the current velocity field. Now, I highlighted a few words that I think are important in that definition. The first one being velocity field. Can anyone in the crowd tell me what a velocity field is? Yeah? Awesome. That's exactly that. And that's, as you said, it's a grid with unit cells, and in each and every of these cells, we have a little vector, and that vector has a direction and a magnitude. And that vector represents a velocity. If it's not quite clear yet, just hold on, it will make a lot of sense in just a second. Now we take steps in time. That's quite convenient because that's how our game engine works, right? Like every frame, we render a new image, and that frame is separated by, say, 16 milliseconds from the previous frame where we do another simulation. And if you, for example, take a glass of water and splash it on the ground, it's quite expected that the water just not stuck in the initial position. It actually flows in a very fluid-like motion. Well, that's what we do when we take steps in time. We simulate that movement across time. And here we have, for example, the green arrows representing our previous state and the black arrows representing our new state. And finally, we tie all of this together with fluid simulation. And at that point, fluid simulation is just a matter of moving a quantity through that liquid. That orange dot is going to move through our velocity field, following the little velocity vectors in order to, across time, arrive at a new position. That's how it can look like. That's a representation of a velocity field. In that case, it's an inside normalized representation, where I chose to have on the red channel the x-axis of my vectors, and on the green color, the y-axis of my vectors. So it's kind of pleasing to look at. Right. So now, if you know me or talk with me a little, you know that one of the things I really like to fight against is that ideas that graphics engineers must be math genius. You know, like if you are not a math genius, you have no place being graphics engineer. Well, that couldn't be further from the truth. And actually, that's what's preventing a lot of very talented people to come into the field, because they're actually afraid that they would not fit in. And that's because we like to push academic papers really high. So, yeah, like you need to read the academic papers at breakfast, otherwise you're like just not suited for the job. I'm going to be honest with you, I don't like to read academic papers, and that's actually when I'm starting a new topic, the last thing I do. Because we are lucky enough to have lots of resources online, conferences like IGDC, put all their processing on YouTube's, or GDC on the GDC Vault. And what you can find there is what the industry is using, right? Might not be exactly what was shipped in the game, but it gives you an idea of what they looked at, what worked, what didn't work, and maybe what direction you should pursue. And you have also conference, Eurographics, SIGGRAPH, just to name a few. Next, I like to look at GitHub implementations, right? I mean, the number of repository of people having done things before is just incredible. Be mindful of the licenses, but that can give you also an idea of what the industry or like what people are using and how these algorithms are being implemented. Also like to look at industry books, GPU Gems, GPU Pro, good source of resources. And finally, I look at academic papers. And really the thing is, the problem with academic papers is you have to read them multiple times in order to understand. You have to read all the literature around because they reference each other. And oftentimes what you find inside these are not implementation ready. You still have to do a lot of work around in order to get it in your application. That's kind of my process when I'm starting in a new topic and I want to understand what's going on. And for fluid simulation, in that case, Navier-Stokes seems to be a good direction to follow. So at that point, I think we're ready to start with some early implementation. And for that, I like to do a sketch. Take a piece of paper, a little pen, and I start to draw something. In that case, we have processing the physics input, that's the input to our system, doing the Navier-Stokes simulation, and finally using that in a shader or a material in Unreal terms. I'm not going to cover the physics input because that's slightly tangential to the talk and not really on topic. And I'm more going to focus on doing the Navier-Stokes simulation, doing the fluid simulation itself. Now, if you are a junior or even like a senior for that matter, when you start with Unreal and you have like no knowledge of Unreal, it's extremely intimidating. Like we're talking about 60,000 files, more than 1 million lines of code. Where do you even get started in all that mess? Well, I'm going to give you a few tips and tricks here and there to help you in your discovery, but really we are lucky with Unreal that we have some documentation to help us get started. In that case, I pulled that one, creating textures using blueprints and render targets. I seem to be quite close to what we want to do. We want to create a texture with the result of our fluid simulation, and blueprints let me think that I can do that programmatically. So if there is a blueprint, there might be some code behind it. And here is biggest secret of all. You don't need fancy tool to do any of this. Like a simple string search will get you a very long way because I can get that raw material to render target, feed that into the string search, and voila, I have the function that is actually doing that. And from there on, I mean, you are really playing some kind of game of following the clues, right? You are Sherlock Holmes trying to figure out what's going on in your code. So here I have draw material to render target. And let's look at the first clue. It's a bit small, but bear with me. At the top, I highlighted a line that says texture render target, game thread, get render target resource. Game thread. Okay, that's interesting. That's because Unreal is actually a multi-threaded engine. Lots of threads doing a lot of things at the same time. And for that matter, we're only going to look at two. The game thread, that's where we execute most of our game's logic. When you do onTick or all of these kind of things, that's executed straight into your game thread. And next to the game thread, we have the render thread. And the render thread is the one generating all your rendering commands, managing all your scenes, and doing all of these kind of things in order to get the images on the screen. And actually do note that it's not the one that is talking straight to your hardware, to your Vulkan, DirectX, or OpenGL. That's not the one. There is another one, the ARHI thread. That's slightly off topic. And by the way, all of these timeline captures was done with the Unreal Insight. It's a tool that is baked right into Unreal. If you look at the bottom of the interface, you can pull it. And I really do encourage you to use it. All right, so if we come back to our code, we have our game thread, get render target resource. We understand a bit better what it's doing now. And we can look at another piece of code, which is enqueue render command, and then a lambda function. That's interesting because that seems to be the mechanism used by Unreal in order to pass something from an actor, from the game thread, into the render thread. And after that, we have a draw material. Seems to be what is actually doing the draw. So let's follow the reference. And here we are, render tiles. OK. Let's get some cues out of this. We have RDG GPU stat scope. RDG seems to come back often. And we have add pass. OK. Now, does any one of you have experience with Unreal rendering and RDG in general? Show of hands, anybody? Perfect. So, what's RDG? It's in Unreal, it's a rendering dependency graph. So you might be familiar if you've done any kind of OpenGL programming in the past, of how you structure or how you build a frame. You depth pre-pass, you forward pass, you pass effects, and you define all of that explicitly in your code, right? Like you write them, one goes into the other and into the other. Well, now the industry is moving towards some kind of more graph approach, because when you think about it, all of these passes can be defined through a graph. And that has many advantages. It lets the computer being able to implicitly schedule all of that and manage your resources for you. So, for example, if we take a depth pass, in that case, a depth pass generates a depth target. And that depth target is generated by the depth pre-pass. It's used for the SSAO, and then it's used for the opaque. But from that point forward, after the opaque, you don't really need your depths anymore. That's not required information. So the algorithm behind the graph is able to say, okay, now I'm dropping the depths, I deallocate that memory, and I can reuse it later for something else. That allows us to have like much better and much higher resolution for a lower memory footprint. I will also bring your attention to the fact that the SSAO block there the screen space ambient occlusion block is overlaid with a shadow block and in a different color. And I want you to keep that in the back of your mind, and we will come back to it, I promise. All right, so if you want to know more about RDG, in Unreal, you can check the RDG 101 crash course that you can find on their website. Or if you're interested more in render graph in general, you can also check the Activision presentation that they did at REAC 2023 on YouTube. Okay, so we have new knowledge. It's time to update our little sketch. So we process our physics input, we enter our rendering thread, we create a rendering graph where we'll define all our simulation steps, we do the Navier-Stokes simulation, and finally, again, we use that in our shader. And we can start with a bit of code. I think we know enough about how it works, or at least enough to continue to stumble our way through the code. And I will present some example of an implementation of that. Bear with me. I don't want you to understand or like memorize all of this. That's not the point. You can watch the talk online afterwards if you want to come back to a reference. But I just want to prove to you that it's actually quite simple to get started and get your first result in the engine. So let's start by defining some context parameters. In that case, viscosity, dissipation, all the kind of things you may find in your fluid simulation. And we pack all of that, and we send that to our rendering set. Right? You see at the top, we are on the onTick function. We are in the A actor, and that is living on the game thread. And now we need to pass all that data and start the execution on the rendering thread because we are doing some rendering stuff. Enqueue render command, we find it again, and we have a little function that we are calling. So let's bring that function. Here we have, we create the render graph that we need. Very simple, graph builder, we invoke it, and we start to build our graph. And we declare some resources for that graph, okay? We want to work on some textures. And there is something actually quite important to know about our RDG managed resources. Because you have two types of resources. So if you remember when I was talking about the graph and how it works, one of the big advantages, the graph is able to know when to allocate and release resources. And you do that by defining a transient resource. The transient resource lifetime is constrained to the graph. The RDG graph is managing when to allocate, when to release, and when to alias, reuse that memory for something else. Or you can also have an external resource. And that's a resource which lifetime extends outside the graph. Think about something that you want to back up across frame and reuse multiple times. In that case, it's your responsibility as a graphics programmer to initialize that resource using RHI and release it when you don't need it anymore. Okay, so back to that. We have our two resources. The first one, which is an external texture, it's our velocity source, and that's something that we want to keep across many frames and continue to update. And then we have our second type, which is transient resources. That is the velocity destination. That's something we're going to work on, update as we go inside one frame, so that we can let the graph builder just discard it whenever it wants. We have our execution function, and we come back to this in a second. And finally, we execute the graph. And that is most of it for the graph builder. What we just need to do is schedule some work into it. And that's how we do that now. We set up the shader. And you might be familiar with shaders in Unreal with material graph, right? Like, who has experience with material graph before? Right, quite a lot of people. And the problem with material graph is, well, you cannot really do compute shader, or you cannot really plug it in your custom rendering. So for that, we need to define shaders. And we'll come back to this in a second. So we set up our shader. And finally, we emit the draw code, fcompute shader utils, add pass. And with that, you have now a compute shader schedule into your timeline. The IGDC defines a lot of little helpers for this. You have helpers to add a compute shader. You have helpers to do a full screen triangle. You have helpers for all of these kind of things. So do use them. They are very convenient. But as I say, we need shaders, right? Like, we need to prepare our shaders. So how do we do this? We define an fglobal shader, very simple. We have a little bit of a macro at the beginning to declare the shader inputs. In that case, target size, delta time, right, the time since the previous update, or like the different textures the shader is going to work on. And then we link the file, Unreal shader file.usf. That's what the system is going to look for on disk for your shader. And that's as simple as that, how you declare a new custom shader in Unreal. But what do we actually put in that shader? I mean, that's a good question. And it's time to look a bit more at fluid simulation. So I decided to pull a random state in our simulation that's somewhere in the middle. And the first step we're going to do is a step called advection. Now, advection is a very fancy word to say just stuff moving in a liquid, right? Like, as simple as that. And if we think about how stuff move in a liquid, we have a velocity field here, we have our little vectors, and we're going to look at the one top right over there. Right, so that if we take that velocity, we apply, we take that quantity and move it, it's going to move somewhere there in bottom left. And that is, we can solve it, simple, explicit differential equation, no problem with that. I mean, it's just extremely scary just to say we're just moving things. But the problem is, like, this cell is not the only one actually influencing that bottom cell, right? Like, we have all of these three other cells that are going to participate in the result of that one. And if you've done any kind of GPU programming, that's where you start to be scared, because if we are looking at the cell or the pixel top right, and we need to synchronize all of these in order to write to this one, that's atomic operation, and that's recipe for very bad performance. So some very, very smart people found out that you can actually solve it backwards through what they call an implicit solution. And instead of looking where that quantity went, it's actually simpler to look at where that quantity came from. So we take our vector, we reverse it, we look in the other direction, sample the 4 points, and voila, we're done. How does it look in code? Well, that's our shader in Unreal. I know you're probably thinking, like, hey, wait a second, I can actually read that stuff. It's not that complicated. For sure, I mean, it's just simple HASL. And that's what Unreal used behind the scene, simple HASL with a little bit of flavor here and there just to customize some of the inputs. And very simply, we see at the first line, we sample our velocity at our current pixel, we reverse it, apply it to the position, and sample back, and we have our new quantity. All right, so going back to our fluid simulation, I'm going to go very quickly through that because, as I say, fluid simulation is a very complicated topic, lots to say. But if you want to know more, I really recommend you check the GPU Pro 3 article, Fast Approximate Fluid Simulation. That will give you all the details I use in that talk. So after our advection step, we do a diffusion. Right? A liquid is somewhere viscous. It will diffuse the velocity or the quantities. We establish the divergence, and from that, calculate the pressure field. Use a pressure field through gradient subtraction to apply to a velocity field. And from there, we just do next frame and repeat that simulation every frame. How it can look like, right? One frame to the other. And I promise there will be a demo at the end where we'll show this all moving because it's shiny pixel after all. All right, so in my case, I decided to use Compute Shader to do this. Compute shaders do have some drawbacks. One of them being like if you use a fragment shader, you have something at the end called an output merger. When you write to a random target, it goes through the output merger. It makes sure that you actually have the maximum throughput when writing to that. If you use a compute shader, it's not guaranteed that you're going to write with the best pattern. So you have to maybe do some manual optimization in order to optimize the pattern to get the best throughput. But most importantly, it also breaks random target compression. While all your random target are somehow compressed in memory, so it doesn't use as much space as possible. If you use compute shader, not only does it break the compression for the rest of the frame, but also break it entirely. Like if you use it on the random target, you won't have any compression anymore. So try to limit the lifetime of the resource you are writing to. But one of the main benefits of compute in that case is you can actually do asynchronous compute. So now pull that memory from the back of your mind when I say on the random graph slide, keep that in mind about the SSAO being layered on top of the shadow. Well, what was going on there was asynchronous compute. And the idea is, well, you have some part of your hardware, say, is using the rasterizer or the fixed function pipeline stuff. But most of your compute is staying on the table because rendering shadows actually is not very complicated. So you can use that compute powers that you left on the side for something else. Something else could be fluid simulation, could be SSAO, could be whatever you want. So compute shaders are really great for that. All right, so we have something, and high chances it doesn't work. I mean, like for me, it never works on the first try. I don't know for you. If it does, come and see me at the end. I'm really interested to know how you do it. But when it comes time to debug what you've done, here's a few guidelines to keep in mind. Integrate yourself with your engine workflow, right? Like expose as much debug information as you can, as much control as you can. If you can see the resources directly in your engine, all the better. If you can toggle some things on and off, all the better. But also use some industry tools. Things like RenderDoc, Pix, Insight are great at looking straight into what's going on at a level you cannot really even expose in the engine. And make your life easier. Things like markers, RDG, even scope, can help you define better scopes for things. In that case here, at an iterative process, I need to run 30 times. I mean, RDG is going to put little things saying, hey, you're doing this, 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 but not really pack them together. So think about all of these little things because it's all about reducing your iteration time. Use things like Unreal Live coding features, shader debugging mode, or refresh your shader directly in the engine using that handy little shortcut. Because the more time you spend just recompiling, going back and forth, the less time you have to actually test your hypothesis and try to see if it works. Now comes profiling. And there is one thing about profiling I'm really insisting upon is you are probably the worst person to do performance profiling on your system. And that probably sounds weird, right? Like you wrote it, it works in and out. Why would you be the worst person? Well, because you start to assume things. And I cannot tell you how many times I was like, yeah, I'm sure the bug is there. I'm sure the bottleneck is there. I'm just going to optimize the heck out of that thing before even doing anything because I know that's a problem. It wasn't a problem. So never really assume anything. Always tools. Your specs inside, just look at where it's slow, or the profiler in Unreal, the Unreal Insight. Just use all these tools because that will help you find your problems. And use them often and as early as possible. You don't want to wait for the last week and having to crunch in order to find what your problem is. All right, and then comes time for shipping. Awesome, our system works, debug, running great. Well, we want it to keep running great. So it's time to work with your QA and start thinking of a test plan as soon as possible, right? Your QA is here to help you ship a working product. So make their life easier. You know how the system works, so clear out all the basics. My system is supposed to work that way, that way, that way. You can check that way. Like these are the list of steps that you can use in order to verify that it works. Here's a level where you can see all the things in place at the same place, quickly check, quick smoke test to make sure that it actually works. Make it easy for them to test so they can actually focus on their work, that is breaking your thing and finding weird way to break your things. And finally, I mean, that might sound obvious, but really do test on many setup as possible. Different hardware, different scenarios, because things might work well on NVIDIA and not on AMD or the other way around. It's, when you're working with graphics directly in that fashion, high chances is you might do something that is the driver is not liking or slightly wrong. And in that case, well, it might work on one and not on the other. Right, and so just before we move to questions, I promised a little demo. So all of what we presented here, I can actually go in the engine, pick up a little gun, and start firing at the surface. And that's all the steps I described here. It's simple. It's little fluid simulation running straight into Unreal. And you know when I said about having well-integrated and easily accessible configuration options, well, if our art director comes and say a little bit more, a little bit more magic on that surface, I can easily come in my component right there. I can say, okay, I'm just about to add some layers and say, what about some local vorticity or a vortex, right? A vortex in the middle. I schedule that correctly. Maybe I want the vortex to be a little bit more powerful. I can jump right in again. I didn't write any code. And we have the same simulation with a nice vortex in the middle. All right. So that's some references. If you want to check them, again, you can check them on YouTube afterwards. And I think it's time to open the floor to questions.
Hi, so that was an amazing talk. I have a couple of questions. So the first one is you're talking about transient resources. So it's a bit going to go away from Unreal. When coming to Vulkan and DirectX, creating, destroying the descriptor sets every frame would be very expensive, right? So in that case, would you still destroy them at the end of the frame, or uh, or would VMA and DXMA would take care under the hood? How does transient resources work in such a scenario?
So I'm trying to think about a good answer because it really dives down into very technical territory quickly. But the idea is it's not actually destroying the resources. It's just aliasing with a memory or something else. So it just creates another descriptor that's going to point to that resources, or like that chunk of memory that was allocated for your resources before. So that's not so much of a performance issue in that case. And for the other resources, well, it's up to you to know when it's fine to release it or recreate it.
You were also talking about render target does not get compressed from when we output from the compute shader. So is it specific to Vulkan and DirectX, or every API does that?
It's to every API. The problem is when you write to a compute shader, there is fewer assumption that the system can take, right? Like you do as a square bracket notation to say, I want to write that to that exact index, that exact pixel. It's, when you go through the output merger, it's able to do a little bit more magic in order to optimize that and work in tiles or stuff that makes it easier for it to do that kind of compression. So any kind of compute will remove your compression regardless of the API. Or it's an API, I don't know yet.
Thank you.
Hi. This isn't specific to fluid simulations, but rather with regards to compute shaders. So I just wanted to ask, under what contexts would you consider using a compute shader? Are there specific contexts, or is it just something that you do whenever you realize that there are ways to optimize computation?
It really depends, depending on what kind of feature you want to use. If you want to use some kind of heavy wave intrinsic space, like that's typically the point where, if you do scene management or culling, and it's not directly related to a pixel, obviously compute. When you're in that gray area of like post effect, for example, where you're like, okay, that works on a pixel. Is it better compute or is it better fragment? It's profiling time, I suppose. Write the quickest for use and profile.
All right, thank you.
I mean, if you have any specific use case in mind you want to discuss, come and see me at the end and we can.
So, hi, Thomas. I just wanted to add something to you, if it's fine.
Yeah, go ahead.
So, with regards of using compute shader that you asked, right? So, my take on that is you can use it for any data manipulation, because one of my earlier projects was volumetric lighting in Unity, and we created a volumetric lighting system, and we used compute shaders to do a ray march. So, it's all up to you. Treat it as a shader that you can use to do parallel processing. That's it. But yeah, that is, thanks, Thomas.
Yeah. There's more? Wow, okay. But
So your projects, anything you would like to share with us?
I don't know. If you want to ask questions, anything about human rendering, that's also something I've done. More on hair rendering, strand-based hair rendering. That's a big topic of interest of mine. It's like wrapped up a little bit, but that's yeah. Otherwise, now I do mostly consultancy.
Hi, Thomas. Great talk.
Thank you.
I have a question. I understand that this is an advanced talk, but for some beginner resources for getting into Unreal flavor of rendering, is there something you'd recommend? Any references, resources?
So I guess the IGDC 101 covers quite a lot about Mandelgraph and how to get started in that specific area. For the rest, for me, was mostly just doing search and following reference in the code. I know it's not the most beginner-friendly, but I mean, there is a couple of GitHub repos I didn't link in there, but that try to explore a bit, but some of them are complete to a point and then suddenly stop because the guy never
Maybe
updated
some kind of beginner API references, something like that. Especially for someone who understands rendering,
Yeah.
but not the Unreal APIs of it and such.
So the Unreal rendering API are quite close to what you would expect from DirectX. It's DirectX mixed with Vulkan in very understandable fashion in that way. So if you understand enough about rendering, just check up the IGDC 101 and follow that course. That's why that presentation was made in that way, that you can take it and reference the slides and then understand enough to get you on the right track.
All right. Thank you so much.